Winds. What causes them? Air is a fluid, so it easily moves from place to place. Differences in air pressure cause that movement. Wind is the movement of air parallel to Earth's surface. Wind moves from areas of high pressure to areas of low pressure. Most differences in air pressure are caused by unequal heating of our atmosphere. Convection causes winds. Remember that we've discussed convection in the past. Convection currents form when an area of Earth's surface is heated by the sun's rays at a different rate than other areas. So as air over the heated surface expands, it becomes less dense. As the air becomes less dense, its air pressure decreases. If a nearby area is not heated as much, the air above the less heated air will become cooler and denser. More dense air sinks. So the cool, dense air with a higher pressure flows underneath the warm, less dense air. This forces the warm air to rise. Measuring wind. Winds are described by their direction and speed. They can blow from all directions. We measure wind speed and direction with a device called a wind vane. The wind swings the wind vane so that one end points into the wind. The name of the wind tells you where it came from. We always name winds based on the direction that they are coming from. So for example, a south wind blows from the south, and it blows toward the north. And a north wind blows to the south. An anemometer. Wind speed can be measured with an anemometer. It has 3 or 4 cups mounted to the end of spokes, and it spins on an axle. The force of the wind against the cups turns that axle, and there is a meter connected that helps to measure wind speed. So the picture you see here shows an anemometer, and based on the direction of this anemometer, which direction would the kite be flying? So if the wind vane is pointing to the right, that means the direction that the wind is coming is from the right. So if you were flying a kite, which direction would the kite be flying? It would be the kite on the left, because the wind would be blowing from the right to the left. Wind chill factor. On a warm day, a cool breeze can be refreshing, but during the wintertime it becomes extremely miserable. We call this wind chill factor. The wind blowing over your skin helps to remove body heat. The stronger the wind, the colder you feel. So if a weatherman reports that the temperature outside is 20 degrees Fahrenheit, but with a wind speed of 30 miles per hour, the wind chill makes it feel like 1 degree above zero. This is part of the reason why we oftentimes have days during the winter where we end up without school. If the temperature gets to, with wind chill, to negative 20 degrees Fahrenheit, we are required to close school. How do local winds and global winds differ? On a summer day, we usually have a nice breeze that comes off of a beach or comes from the water onto the beach. This can occur even if there's no wind inland. This is an example of a local wind. Local winds are winds that blow over short distances. This is due to the unequal heating of Earth's surface within small areas. Usually this is due to water temperature differences between land and the water itself. These winds only form when large-scale winds are weak. We call these either sea breezes or land breezes. A sea breeze. During the day, the land warms up faster than the water. The air that's over top of land becomes warmer. Because it is warmer, it is less dense. The less dense air starts to rise. And this creates a low pressure area at surface where all of that air is rising above. Because there's a low pressure area, warm air from over top of the water moves in, or cooler air over top of the water moves in to the area that the warm air vacated. A sea breeze or a lake breeze is a local wind that blows from an ocean or a lake onto the land. A land breeze. At night, this process is reversed. The flow of air from land to a body of water forms a land breeze. So the land cools off faster than the water. Water retains heat over nighttime. So the air over top of the water is heated at nighttime. That air that is heated becomes less dense and it rises. It creates an area of low pressure. That area of low pressure allows that air over top of the land that is cooler to move in. So the air ends up moving from the land to the water. I used to experience this a lot when I lived up north. I used to live just off of Lake Michigan. You could actually see Lake Michigan out of my front window. I would go deer hunting at night, and when I first would be deer hunting, the wind would be blowing one direction. It would be coming from the water. As it got closer and closer to dark, you would always, every single night, notice a difference in the wind direction. Because as the earth started to cool down and the water gave heat to the air above it, the wind direction would cause the air over the land to start moving over top of the water instead of what it was doing all day long. So it became very difficult to deer hunt and figure out where to sit based on that land breeze and sea breeze. The deer would be coming in from a direction that would be, during the daytime, would not cause them to smell me, but then once it got to be later in the evening, closer to dark, the wind would change directions, and if they started coming in from that direction during that time, they would end up smelling me because the wind was blowing directly to them. Global winds. Global winds are winds that blow steady from specific direction over long distances. Like local winds, global winds are created by the unequal heating of Earth. The difference is, though, that global winds are large scale. In the middle of the day near the equator, the sun is almost directly overhead. Those direct rays from the sun heat the Earth's surface intensely. So we get a lot more heat production at the equator when the sun is directly overhead. Near the poles, the sun's rays strike Earth at a much lower angle. Therefore, the sun's energy is spread out over a much larger area. And therefore, it heats the Earth's surface less. As a result, temperatures near the poles are much colder than they are near the equator. So looking at this picture, the angle of the sun's rays cause temperature differences at Earth's surface. Which area on Earth receives the most direct light from the sun, and which areas receive the least? So we should label this based on which is most directly heated and which ones are least directly heated, and then medium directly would be somewhere between the two. So most directly heated is the equator. Sun's rays, as we can see in this picture, they're spread over a very small area. Due to the curvature of our planet and also the tilt, we have a larger area that those rays are hitting as we move away from the equator. So we get a medium directly, right directly off of the equator, or slightly off the equator. The least direct solar radiation, the least direct energy, is going to be this area near the poles where the energy is spread out over a much larger area. Same intensity of energy, but it's spread over a larger area of our planet. Global convection currents. Temperature differences between the equator and the poles produce giant convection currents in the atmosphere. Warm air rises at the equator and cool air sinks at the poles. So thinking back to our air pressure simulation lab, we saw where the water near the light was heated. The water that we put ice in on the opposite side of the tank became more dense. It sank. The heated water rose. The cool water sunk down to the bottom and flowed back towards the area where the lamp was. The Earth works exactly the same way. So air pressure tends to be lower near the equator and greater near the poles, because where air is sinking, there's going to be a greater pressure on top of you. Where air is rising, there's going to be less pressure. The differences in pressure cause winds at Earth's surface. And those winds blow from the poles towards the equator. Higher in the atmosphere, air flows away from the equator towards the poles. So it creates a big cycle. Those air movements help to produce our global winds. The Coriolis effect plays into this as well. And recall, the Coriolis effect is the curving of an object due to Earth's rotation. So if Earth did not rotate, our winds would blow in a straight line from the poles to the equator at Earth's surface. Because our planet is rotating, global winds do not follow a straight path. Earth rotates from west to east. And so this makes our winds have a curve. The way Earth's rotation makes winds curve is called the Coriolis effect. Because the Coriolis effect, our global winds in the northern hemisphere gradually turn toward the right. So a wind blowing toward the south gradually turns towards the southwest. In the southern hemisphere, winds curve towards the left. So a wind blowing towards the north gradually turns to the northwest. So looking at this picture, and with what I just discussed, what direction would the Coriolis deflect global winds in the northern hemisphere and the southern hemisphere? So if there was no Coriolis effect, our winds would sink from the poles and flow back to the equator to be reheated. But because there is a Coriolis effect, we get a deflection. If the wind is flowing from the north to the south, it would be deflected to the west slightly. If it is flowing from the south pole, towards the north, it's going to be deflected to the left slightly. The wind belts on our planet, again, are due to Coriolis and the uneven heating of our planet. The doldrums. The doldrums are an area of calm where warm air rises. The doldrums are found at the equator. On your notes, please label where we would find the doldrums with this picture you see inside of the presentation. They occur at the equator where the sun heats the surface strongly. Warm air rises steadily, and it creates an area of low pressure. Cold air moves into the area but is warmed rapidly and it rises very quickly. Therefore, there is very little wind at the equator. The horse latitudes. The horse latitudes were named by sailors. The horse latitudes are two areas of calm, sinking air. Latitude is the distance from the equator measured in degrees. The horse latitudes happen at 30 degrees north and south. Again, label these in your notes. Both of these areas, there's sinking air, so it creates areas of high pressure. Areas of high pressure do not allow formation of clouds. So there's not much condensation in these areas. Where we have sinking air, there's also usually very little wind. It is very light and variable. The horse latitudes were named by sailors because when they got into the horse latitudes, the wind was so light that the ships that they were trying to sail did not move very fast. Sailors didn't usually supply ships with a large enough amount of food and other things to make it very long at sea. So what would happen is, if they ended up in the horse latitudes, they had to make the ship lighter, because if they didn't make it lighter, it wasn't going to move very fast. The things that they typically had that were really heavy and easy to get rid of in these areas were horses. So the horses got dumped off in the sea, so the boat would end up becoming much lighter, and therefore it would be able to move much better. The trade winds. Again, the trade winds were named by sailors due to them being used to trade. The trade winds blow from the horse latitudes towards the equator. As cold air over the horse latitude sinks, it forms a region of high pressure. This causes surface winds to blow, so that high pressure that is sinking right here is pushed back towards the equator, and again, because of Coriolis, it is deflected to the left. The winds that blow towards the equator are turned west by that Coriolis effect. And notice that trade winds come from Europe over toward the Americas in the northern hemisphere. So the trade winds were used for the trade routes. The prevailing westerlies. We live in the prevailing westerlies. They blow from west to east, away from the horse latitudes. In the mid-latitudes, between 30 degrees and 60 degrees north and south, is where we find them. These winds are deflected to the east, so the wind comes from the west due to Coriolis. The polar easterlies. The polar easterlies blow cold air away from the poles. Air near the poles sinks and flows back towards the lower latitudes. The Coriolis effect shifts these polar winds to the west, producing the polar easterlies. So here and here, remember that the winds are named based on the direction that they come from. So a little bit of review real quickly here. The Coriolis effect and other factors combine to produce a pattern of wind belts and calm areas around Earth. Match the descriptions of the global winds with their location on our planet. So the doldrums. Letter A. We would find the doldrums at the equator. The horse latitudes. Remember, this is the area where sailors kicked horses off the boat because their vessels did not move very fast. They are found at 30 degrees north and 30 degrees south. The trade winds are the winds that were used to trade with the Americas, so they are the winds that come towards the Americas. They are C. The prevailing westerlies. We live in the prevailing westerlies. They happen between 30 degrees north and 60 degrees north. They are D. They also happen between 30 degrees south and 60 degrees south. And finally, the polar easterlies. These are the winds that blow out of the east. They flow towards the west. They happen in the polar regions, both north and south. They are E.